Hello everyone. We will now talk about the Burnside theorem in group theory, which says that any group of order p to the power a and q to the power b, where p and q are primes, any group with order like this is solvable. It's a deep result in group theory, and you can see that it really says a lot. Uh, Moreover, the proof of this theorem is done by using the properties of characters and representations of groups. In fact, these are classic examples that shows the power of representation theoretic techniques. Okay, so we will go ahead to this theorem. So the proof of, we have already stated the theorem. So in order to go ahead to the proof, we have to first have some preparations. So at the very outset, we will talk about a little field theory. Okay, so let's do that. Let's start with a field K. So an embedding of a field K into a field L by an embedding, I shall always mean a homomorphism from K to L. Okay. Let's recall that any homomorphism from a field to another field is automatically injective because the kernel of the homomorphism being an ideal of K, it can either be trivial or whole of K, but whole of K certainly cannot be there because 1 goes to 1, so if the kernel has to be trivial. Okay, so whenever there is an embedding of K into L, we have a subfield of L, which is namely the image of K so by the map sigma. So you have a subfield of K which is isomorphic to K. So once we identify the field K with its image, so then we can regard that K is contained inside L. So in that spirit, we sometimes call this also like the following, that we call whenever we have embedding of K into L, we also call it K. L is an extension of K. So the reason, the spirit for calling it an extension, I have just explained, because then you see L contains a subfield which is isomorphic to K. So therefore, once you identify that, you can regard that when L is a field which is containing K. So in that sense, you can say that L is an extension of K. And once it is there, then L can be realized as a vector space over K. So the dimension of this vector space is called the degree of the representation. So if the dimension is finite, so that positive integer is called the degree of the extension, and we denote it by the following notation. So we denote it by the following notation: L over K. Okay. So before we go ahead into more results, let's look at some examples just to understand the concept of this embedding. So first of all, what is an example? Let's look for some classic ones. Q is R is a subfield of C, so therefore you can regard that from Q to R, the usual map. So every R goes to R. So basically, if you have a field which is indeed contained in a bigger field L, so then the map from K to L, the identity map that each X goes to X, is an embedding. Okay, however, so now we also, these are the quite natural ones. So now I will show you by an example that a field can be embedded in a bigger field in a different manner. So what we do is, let's take C. So C is embedded inside C in two ways. It can be embedded, first of all, Z goes to Z. There's also homomorphism from C to C. So the C is embedded inside C. This is the usual embedding. But there is also an on mode embedding. So that's C, from C to C. If you just consider Z maps to Z bar, you see that's also an embedding. So a field can be embedded in a bigger field. Bigger field means it contains the smaller field. It can be embedded in a different way as well. Okay. So let's give another example, which is going to be quite crucial in our discussion. So we will, for that, let's recall that suppose if f is a polynomial with coefficients from k, so f is said to be irreducible if whenever f is written as gh, where g and h both are polynomials with coefficients from x, when both are polynomials coefficients from, then one of them must be constant. So basically, f does not have a proper factorization with polynomials, proper factorization over the field k. So if this happens, then we will say f is irreducible over k. Remember, it's to be on our safe side. It is always advised to mention the field on which we are talking about the irreducibility, because let me try to explain. So suppose k is a polynomial, k is a field and which is contained in a bigger field L, and f is a polynomial with coefficients from k which is irreducible. But when you view f, since k is contained inside L, so when you view f as a polynomial with coefficients from L, there it might be reducible. For example, like if you take q over r, if you take just q over r, so then x square minus 2 is irreducible over k, irreducible over q. But when you view it as a polynomial over r, certainly it becomes reducible. Okay, so now let me tell you what is the connection with embedding and this and an irreducible polynomial. Okay, so if f is irreducible, then we consider the ideal generated by f. Okay, so since f is irreducible, it has to be a maximal ideal. In fact, every maximal ideal of kx will be of this form, because it's a PID and every ideal has to be generated by a single element. So once it has an irreducible element, certainly that ideal has to be maximal. Okay, so it will be maximal. So once this is a maximal ideal, then kx, so once this is a maximal ideal, then kx quotient f is actually a field, because it's true for any general ring. Once you quotient it out by commutative ring by maximal ideal, what you get a field. Okay, so I will now show you an embedding of k into this field kx quotient ideal generated by f, where f is assumed to be an irreducible polynomial with coefficients from k. So what you do is, so every element, if you say, let's say a typical element, if you want to write it by alpha, so send alpha to the coset of alpha, which generally we write by alpha bar. Okay, so then you can just check that this is indeed an embedding. So thus q is thus every field is embedded in the field obtained by considering the quotient modulo the ideal generated by an irreducible polynomial. So for any reducible polynomial, we can irreducible polynomial with coefficients from k, that is irreducible polynomial over k, we get such an embedding of k. Okay. So we have seen some examples of embedding. As I said, let me just recall you another. So whenever you have an embedding, another way of saying that same thing is, when you have an embedding of k inside L, another way of saying this is L is an extension over k. And we explain why it is to be perceived as an extension. All right. So now let's see something. So let's try to, if I just focus our attention on this construction, on this field, so starting with any irreducible polynomial we can do that, but the way it is defined is just as a quotient, which is actually very abstract. Okay, but now I will show you there are certain, there are certain cases where, and such cases are not rare, rather they are perhaps very much common. So there are certain cases where we can indeed visualize or identify such an extension of K. So let's make the following definition that so suppose first let us suppose that K is so L and K and L are two fields and K is contained inside L, and suppose A alpha is an element in L. We say alpha is algebraic over K if there is a polynomial polynomial over polynomial having coefficients over K. So since K is contained inside L, you can consider F as a polynomial with coefficients over L. So then you can talk about evaluating the polynomial at alpha. So this is what the definition says. So I will say an element alpha in L algebraic over K if there is a polynomial with coefficients from K which has alpha as a root. Okay. Now from here, the first thing that immediately follows is the following one, that so if being a polynomial in the PID, so f can be written as a product of irreducibles. So if f alpha is 0, then at least one of the irreducible factors of f must have alpha as a root. So thus what we get is if alpha is algebraic over k, then there is an irreducible polynomial. In fact, you can make by dividing it by dividing by the inverse of the leading coefficient, you can further assume that the polynomial that you consider is a monic one. So thus we can say that if alpha is algebraic over k, then there exists a monic and irreducible polynomial such that f alpha is 0. Okay, so in fact now the converse is trivial. So if there is a monic irreducible polynomial, so then automatically alpha has to be algebraic. So thus then the definition, when we just said that there is a polynomial such that this happens, that condition we can replace, in fact further replace that there is a monic irreducible polynomial such that this holds. Okay, such that f of alpha is 0. So if that happens, then we will say alpha is algebraic over K. Now let me give you an example. For example, root 2 is algebraic over Q in the extension Q over R, right? So in fact, what you can show is, though I will not prove it right now, suppose you have an algebraic integer, okay? So an algebraic integer by means automatically there is a polynomial, there is a coefficient with, there is a polynomial with integral, monic polynomial with integral coefficients, okay? So automatically every algebraic integer is algebraic over Q. I mean every complex number which is an algebraic integer automatically gets algebraic over Q. Okay. So let's before going ahead, let's make one more observation that given if alpha is algebraic over K, then this monic irreducible polynomial has to be unique. So why so? Because if that's very easy to see. In fact, we will see it right. We will see it now. That let's look at it from a different perspective. So suppose that K is algebraic. K is next embedded inside. So K is a subfield of L. In fact, here we assume that just proper containment. It's just containment, not just an embedding. So and alpha is in L. So we define K alpha to be the smallest subfield of L containing K and alpha. Remember here smallest is not in the sense of number of elements, rather it says that if any other subfield contains both K and alpha, then that must contain K alpha. Okay. For example, let me give you this, that what is Qi. Qi is the smallest subfield that contains both Q and I. You can immediately check that has to be A plus Bi, where A and B in Q. All right. So suppose alpha is algebraic. So that means there is a polynomial f, which irreducible polynomial f monic, which has alpha as a root. So what we will do now is we will consider a homomorphism from kx to k alpha. How is that homomorphism goes? So if you consider a polynomial a n x to the power n and so on and so forth, then that maps to just evaluation at the point alpha. This makes sense. You just check that this indeed defines, this indeed is a homomorphism. So now what we do it, whenever there is a homomorphism, we will to consider it, we will apply the first isomorphism theorem on that. So therefore what we get is kx by module by the kernel of the homomorphism. Now since alpha is assumed to be an algebraic, so that means there is a irreducible monic polynomial such that f of alpha is 0. So let's call so let f be irreducible monic polynomial, because we know there is one such that f of alpha is 0. Then you see the kernel. So the kernel of this homomorphism, kernel is contained inside f, and kernel, so since kernel is an ideal, so it has to be generated by a single element, right? And we have an irreducible in that. So from here it is now immediate that kernel has to be generated by f from the irreducibility of f, because kernel is generated by a single element. So and f is there, so f has to be a multiple of the generator, right? Now since f is irreducible, so then that must be f must be an unit times the generator. So therefore f itself can be regarded as the generator of them. So from here to k alpha, I have a map after using first isomorphism theorem. So this is a now this is now a 1-1. This is a 1-1 ring homomorphism. Okay, but since this is maximal, so this guy is actually a field. So therefore its image will be a field. Now let's see one more thing that in fact that gives me the way how to see this k alpha. So we have the following from kx to kx modulo. So if a polynomial, let's call it, if we call it phi x, so a polynomial is by the quotient map, it is getting mapped to phi plus the ideal generated by f, right? And now first by first over second theorem, of course, this diagram commutes. So a typical phi, it just sends to on the where if a phi is here, so here it goes to phi alpha, right? Now, first of all, let's make from here several things will follow automatically. So, since this is a field, image of that will be a field. Now we will see one more thing. So, since this is the so under the quotient map, so what happens to the constant polynomials here? So, a typical constant polynomial R will come here. So, will come here to R plus will come here to R plus the ideal generated by F, and that here goes to R itself because because of the congruity to the diagram, because R here being evaluated at alpha goes to R. So then what's the lesson? Lesson is the following, that the image naturally, so image is a field that contains that what are the things that contain, so that contains of course k, and also that contains alpha, because in the evaluation map x maps to alpha, so alpha is in the image. So because as I said that under whenever I have applying first isolation theorem, the image of that is same as the image of this. Okay, so there's a so the image contains both k and alpha, and images has to be a field. So from the definition of k alpha, that it is the smallest one, it follows that this map is in fact in particular onto. So thus this becomes an isomorphism. So in the special cases when f is f is yeah, f is such that there is an alpha which is a root of f. Of course, if an irreducible polynomial f is such that there is an alpha in L such that f of alpha is 0, then this quotient, then this bigger field which is obtained by quotient, obtained by considering the quotient like this, can be it can be actually perceived as this. So it can be regarded as the smallest field containing both k and alpha. Okay, and from here also one more thing is clear, that the choice of this f is unique, because if you see, if there is, if let's say g be another polynomial, another irreducible monic polynomial such that g of alpha is 0, then g also will be inside the kernel, then f has to divide g, but since they are both monic and irreducible, g has to be same as f. So in view of that, it is legitimate to say that the monic polynomial of alpha for every algebraic alpha belonging to L, because we know that there is one, and that has to be one and only one. Okay, so let me give, before we go ahead, let me give an example. Let me talk about a special case where every element is algebraic. So what we will do is, let's make a definition that if k is a subfield of L in such a way that every element in L is algebraic over k, then we call it an algebraic extension. Okay, so for example, this qi over q, it's an algebraic extension. Okay, so now we will see that every finite extension, if you want to give a nice class of examples which will be always algebraic. So the first thing that comes here is the every finite extension is algebraic. But so basically, suppose finite extension means the degree of the this is finite, so let's call it n. So we will now consider the set 1 alpha alpha square up to alpha to the power n. So this is a set of n plus 1 vectors in L. Since the dimension is L, so therefore it can this set cannot be linearly independent. So there will be a combination, non-trivial combination of these elements, which will be 0. So from that we get a polynomial, which a polynomial with coefficients from k, because here the combinations will have coefficients from k. So get a polynomial with coefficients from k, which is alpha as a root. So thus every finite degree extension is an algebraic extension. And the converse does not hold, but we won't get into that. For us, we will always deal with finite extensions. So let's not worry about the infinite extensions of having degree infinite. Okay. And also I will now tell you and as I said that when I define degree of an extension, then I should have mentioned that this degree has a very nice formula. Before I forget, so let me first tell that. So suppose there are two extensions, let's say a k l and L is let it be F. So then F is an extension over K of K. So the degree of F over K is the degree of F over L and the degree of L over K. It's also very easy to see that. In fact, I mean, in this video, we will be, what I'm doing is I'm just quickly reviewing the facts from group field theory that we needed. Because I presume that you, at least, if not all, most of you must have seen this stuff in your MSc. So I'm just I'm just in picking up those things which will be required in our consideration. So it's also very easy to prove that suppose L over K has the basis V1, V2, Vn, and F over L has the basis W1 up to Wn. Then since this is the basis of F over L, so every element in F can be written as a combination of W1 up to Wn with coefficients from L. Now every coefficient in L can be written as a combination of them. So therefore, when we write every coefficient of these Wi's as a combination of Vi's, so all total what we get is this set Vi times Wj ij, that turns out to be from what we have just said, a spanning set of this vector space. Now it's a very trivial checking that it's indeed linearly independent. Thus this is a basis of the vector space F over K, hence the dimension of this is same as product of the dimension of this and that. That shows this formula. All right, so far so good. We have discussed what algebraic extension is. We also discussed this thing. So before we move further, so let me just let's just note one thing that under this isomorphism, so under this isomorphism, so x bar, which is the coset of x, that maps to alpha. Okay. So we will also talk about this thing. in fact a very elementary observation which says that this is simple, that suppose suppose K is isomorphic to K prime, then if f is an irreducible polynomial over K, we can talk about sigma f. What is sigma f? If f is a n x to the power n, a 1x plus a naught, then sigma of f will be just applying sigma on each and every coefficient of f. So if f is irreducible, it's easy to see that sigma f is also irreducible, because once there is a factor, from that you can get a factor here. So that means what we get is, so kx by f, kx by f, this is isomorphic to sigma k of x by sigma f. Okay, and under this isomorphism, we have to realize that how this isomorphism works. So basically, if you have a, so what is a typical element here? A typical element here is just a coset of a polynomial like this. Under this isomorphism, that just goes. So you apply sigma on each and every coefficient, then you get a polynomial here, x plus sigma a naught. You just take its quotient. Okay. So again, so far so good. So with all this, we will, so let me just try to recall if I am missing something, because with all this, we will get into the normal extensions of fields. Okay, so yeah, one more thing that I must say, that again, suppose that K is a subfield of L, and let K be f be an irreducible polynomial with coefficients from K, and let alpha and beta belong to L. And suppose that you have two elements alpha and beta in L, both are roots of f. Suppose you have two such elements. Okay, now if you just recall what we have done there, so basically what we have done just here, what we have done just here. So from there, what we can say is, in one hand, I have a, so if I just, in one hand, I have an isomorphism from kx modulo f to k alpha, which sends as a x bar to alpha. And on the other hand, if you just consider beta, then you must have a similar isomorphism like this, which sends this to beta, right? Because that's what we have just seen, that if alpha is a root of the irreducible polynomial f, then from here to here you have an isomorphism. So now, since for each alpha and beta I do the same, so therefore we so if we just now take the composition of these two maps, therefore we get an isomorphism from k alpha to k beta, that's which sends alpha to beta. And also furthermore, we should observe that if I take small k from k, so here it just goes to k plus f, and now if I from push here, it again goes to k. So what I mean is the following, that suppose an irreducible polynomial, for an irreducible polynomial f over k has two roots in alpha, then from that we get an isomorphism from k alpha to k beta, which fixes every small k to small k and sends alpha to beta. So it's a isomorphism that fixes the field k and sends alpha to beta. Okay, all right. With all this, in the next video, we will talk about the normal extension of fields. Okay, thank you.